In this video, we're going to look at the differential relationship between entropy and energy, volume, and number of particles. So we've seen that we can write the entropy as a function of energy, volume, and number of particles. And we can use the multivariable chain rule to write ds in terms of differentials of each of those three variables, where each of our differentials, when taking, say, for example, partial s partial u, we hold the other two variables constant. So we have partial s partial u du, where v and n is held constant, and we have the same concept for the other two variables. And now we've gotten to a point where we have seen that each of these partial derivatives is in fact related to quantities defining the system. Temperature, pressure, and mu is our chemical potential. So what we can do is we can rewrite ds in terms of differentials of each of our variables that entropy is written in terms of, and temperature, pressure, and the chemical potential. Normally this is rewritten as du equals TdS minus PdV plus mu dN. And this equation is super useful because if you know this equation, you can find the derivative relationships between any of these quantities. So for example, if we hold n and v constant, well, if n and v are constant, then dn is 0, dv is 0, and we can simply solve this equation, which gives us partial s partial u equals 1 over t. It's a partial derivative because we are assuming that the other two variables are held constant, so that's why we write it as a partial. For example, we could also find a relationship between the energy and the number of particles. So if we hold the entropy and the volume constant, then ds and dv are both 0, and solving du equals mu dn, we get that partial u partial n equals mu, where we hold the entropy and the volume constant. So this can be really useful if, for example, we have a good way of writing down the energy of a system in terms of the number of particles, and we would like to find the chemical potential, right? So if you know this, you can find any of the derivative relationships that you want. I've written 3 of them here. This is not all of the derivative relationships that there are, but you can find them all simply by picking 2 of the variables and holding them constant. You could even hold u constant, right? So all of these 3 involve the energy u, but you could, for example, hold u constant and n constant and find a relationship between entropy and volume, which in fact is right here. Partial s partial v with constant u and n is p over t. Now let's use our new differential equation here in order to reanalyze the relationship between entropy and heat. So first we'll assume that we do not add or remove any particles from the system, so we can set this term equal to 0. So in the case that we don't add or remove any particles, du equals TdS minus PdV, but du is also equal to Q plus W. Both of these statements are true in general all the time. Now, if work is equal to PdV, or negative PdV, which is true for a quasi-static process, which is a process that is slow enough that the pressure or other variables remain well defined throughout the process. If that is true, then Q equals TdS. Because if both of these things equal du and work is equal to negative PdV, then Q must be equal to TdS. So we saw this equation in a previous video where we said it was true if the volume didn't change, but in fact this tells us that it is true as long as our volume change is quasi-static and this relationship between work and negative PdV holds. So in that case, Q equals TdS or ds equals Q over T. Now, For a non-quasi-static process, it turns out that the entropy created is always greater than the value of Q over T. So here is a simple example of how this works. Say, for example, you are compressing an ideal gas and you do it very, very quickly, not quasi-static. In that case, you could have particles build up next to the piston. So the piston is moving this way very, very fast, much faster than the average speed of molecules in the gas. The molecules can't recalibrate themselves in time such that you have a uniform pressure throughout, and pressure ends up building up on the side of the piston there. So in that case, you are doing more work than PDV would suggest. If you did this slowly, you would be pushing against the average kind of pressure of the gas. But here you have built up excess pressure by pushing it against molecules and having extra molecules build up against your wall. So in that case, your work is bigger than negative PDV. Now, I should note, because this looks kind of weird to have this greater than a negative, remember that for compression, this value with the minus sign is positive. Because as you compress, dV is a negative value. So negative PDV is a negative times a negative gives you a positive value for your work. So you're doing too much work here. And if we look at these equations here, well, if work is bigger than PDV, or negative PDV, then Q must be smaller than TdS because they both have to equal du. So if this is true, then this must be true, that our entropy created is bigger than Q over T. So this equation holds true for non-quasi-static processes. This would also happen if we did an expansion. If we did a non-quasi-static expansion, say we expand it very, very quickly, this equation would still hold true, but now our magnitude of work would be less than the magnitude of this. So your PDV in an expansion would actually be a negative value. Your negative PDV would be negative. You're expanding, you're doing negative work on the gas, but this would be a smaller negative value than it would otherwise be. And again, you would have work would be a larger value, a less negative value than negative PDV. And so Q would have to be a smaller value than TdS in order for them to equal the same thing. So this equation holds whether you're doing expansion or compression. It's slightly easier to think about with compression because you have a positive value here, and this is also positive. But in either case, expansion or compression, if you're not quasi-static, your entropy is going to be larger than Q over T. So in the end, this equation holds for quasi-static, which is most of the things that we'll be dealing with. But if we don't have quasi-static processes, we are in this realm here.